Okay, it's recording now. So I'll mute it and then you're going to.
All right, we good? All right, so I can't tell if it's even getting my microphone input.
Jason, can you confirm that you're hearing audio?
Yeah, see if that works. You can hear me? Okay, awesome. All right, so in that case, my name is Noah Ford. I will be demonstrating my neural net for classifying rice. Is it light coming through fine? Okay. So this is the data set on Kaggle, just for reference. It has two classes, Jasmine and Gonan, so it's differentiating between the species of rice. Here is the lovely data set itself. It has 10 features because ID is irrelevant. It's just essentially the row number, the index of each sample. All of the features are pretty much based on, is it echoing? Okay, is that better? Okay, test, hello. Test again. I don't know what it's going through. Okay, sorry. So there are the 10 features, like I said, they're essentially all based on the dimensions. That's really annoying. I wish I knew how to fix that. They're based pretty much on the dimensions of the grains of rice. And then, like I said, there's the two classes, 1 and 0 representing Jasmine and Gonan. So as for, I guess we'll go to the report first because that'll explain things better. So I have just over 18,000 samples, and it's a fairly even data set. It was, I think it was like 47% of, I think it was, yeah, like 47% Jasmine and the rest Gonan. So to, I don't know if I'll start here. We'll go to this first. So basically how I'm going here is I'm reading the data. I'm split. Yeah, I can. So the X is coming from, I'm just slicing out the class and slicing out the ID because, like I said, that's a useless feature. And then here I'm using a Keras function to normalize it because if you look at the data set, some of them are up in the hundreds, some of them are like just decimal numbers. So that makes them all from 1 to 0. And then the Y data, obviously, I'm just slicing out the class. I'm using sklearn to split out the test data sets. Then here is my actual model. I have 6 layers with 4 of them, being hidden layers. It's using the funnel shape, and it is using, oh, this doesn't seem relevant, but it will be later. I'm using stochastic gradient descent as the optimizer, using 2000 epochs. And then if I go to my results, with those specific settings, it ended up getting around 97% accuracy. Something is interesting with my data set. Stochastic gradient descent seems to not work super well with it. So for example, if I have less layers or less neurons per layer, it gets stuck at around 54% accuracy and just doesn't move even over like many thousands. Like it's probably small, unfortunately, but like for this example, I ran it for 7,000 epochs overnight and it only reached 54% accuracy. So then when I add in more neurons or more layers, as I demonstrate here, it actually does end up going somewhere, usually around 97% accuracy. And then something that I discovered is using a different optimizer, which I have my 2 programs here. So again, when you compile the model, you set the optimizer. And this one, I have it set to atom instead of stochastic gradient descent. And I can use substantially less neurons and much less layers, and it'll achieve the same or better accuracy. So you can see here that after only 9 epochs with just 4 layers, it reaches greater than the 97% that I'm getting with stochastic gradient descent. And then after 100 epochs, I'm reaching around, 98.5% accuracy. So it's significantly better for some reason. I don't fully understand what it's doing differently because I haven't been able to research it enough, but it's interesting that it works much better with my data set.
Adam is much better off.
Okay, gotcha. So then I did my feature ranking with Weka. According to that, the minor axis length is the most significant. You can see basically, yeah, I can. Is that all right? So it's just ranking their importance for determining the class. You can see some of them, it's one of the features. If I were to guess, it would be the width across the grain of rice, but they don't have them specifically identified. It was just like not necessarily better, but it's kind of similar to iris where it determines it has the dimensions of some part of the plant.
So this is to identify the type.
Yeah, it's the species of rice. There's only two. It's the jasmine and gonan. Yes. Yeah.
So the longer.
Yeah, that seems to be the most likely conclusion. And then major axis length, which I think that would be the actual length of the grain of rice, seems to be pretty insignificant extent. I don't know what that represents, but is also insignificant.
Oh, yeah. Minor.
Yeah.
Minor.
Yeah. But you can see here that, yeah, 3 of the features, perimeter, extent, and major axis length, aren't particularly useful, and the rest are increasing from there, with minor axis being the biggest of importance. And then down here, that's just an extra page. I ran the data set through Weka with several of the algorithms, and they all yield roughly 98%, just varying through there. I think one was like, those are also all very good. You can see them down here, precision, recall, F measure, they're all very close to 1. So yeah, Adam was, well, random forest got 98.8%, and then from what I remember, recall and precision were also slightly higher. I don't have F measure displayed in my through the neural net. With the through TensorFlow, you mean? Adam gave me the best at that, and it was in this one. I haven't experimented too much with this because I was mostly focused on trying to make stochastic gradient descent work. So I just had Adam as kind of like a secondary. I haven't optimized it too much, but it just has the 4 layers. With for that one, it was the lowest. It had roughly 98.5 accuracy. For the training, the validation was they're both about the same, since it's. Yeah. I guess I can't scroll over. I can't scroll over on command prompt, I guess. But they are, if I zoom out, I can show that they're basically the same between the validation and. Yeah, recall is, or the validation recall is 99.4. Precision was just under 98%. Yeah. Yeah. And then one of the interesting things is, it'll be hard to find, but if I scroll up, this massive amount here was when I ran the 2000 epochs with stochastic gradient descent, and it took over 200 epochs for it to even change from this 54.82%. Like, I think that's the first time that it actually varied from it, and it was just under epoch 200. However, in the case of Atom, like I showed, it only took, I think it was 10 epochs for it to, yeah, basically it learned much quicker for whatever reason.
So if you think, well, I remember talking there that analogy of the giant.
Yeah.
That's what's happening.
Yeah.
But think about it, the giants have a hard time.
Yeah.
Arriving at. With Atom, it's got optimizations, maybe better randomization. Right?
That's what I was
Of
thinking
the
too.
weight, it's starting in better places, so it gets to the minimum faster.
Yeah.
It could be also that step size learning rate is big at the beginning and it starts to get smaller. The position it doesn't having the same size.
Okay.
You know what I mean?
Yeah.
But it's a good idea. In general, Atom has
Okay.
very. I even think there are people.
Yeah. Because that's obviously what I see in my results as well, is that it's.
So what was your data?
Yeah, it was just over 18,000 samples. And then there's the 10 labels because I sliced out ID. And
10 features,
Yep.
2 classes,
yes,
and then how many?
it was roughly the same, so it'd be like 9,000-ish. Yeah.
Early file.
Yeah. I could, well, I don't think I have Weka installed on here. I'll include that in the report though, but it when I looked at it, it was pretty balanced between the two.
So that's good. So then how that is accurate and
Yeah.
Otherwise. You guys have any questions?
All right. In that case, that concludes my presentation.
Wait.
Yeah.
Go to the
Yep. Yeah, because I guess I could even demo it. I mean, it'll take a second, but like, because what I started with was only 4 layers, and I think it was something like 50, 25. And then essentially it just never improved. I think it was Rice class. Yeah, but I mean, you can see it's just, it doesn't change at all. And like when I kept it, that's what I tested with the 7,000 epochs overnight, and it just never improved the entire time. So something about the data set must require more neurons or more layers for it to actually change. But I can pause that then. But yeah, as you can see, it just never moves.
Oh, you killed it.
I did, yes.
Yeah, right. Insight. Any other questions for Noah? What is the most difficult part of the data set?
Figuring out why it didn't work with stochastic gradient descent. Because that took me a while to bug fix, because initially I didn't have my data normalized. I thought maybe that was it. I got a little bit better results because I think it was either at 50% or just below without normalizing.
And then just do me a favor, go back.
Yeah.
I want to make sure. Go to start at the bottom. You landed there in model fit X, Y, validation X, Y. Very important. Model train X, Y. But eval X, Y.
So what you could do for yours is split it with the sklearn thing. Like,
yeah, exactly.
That's what we did with Iris, I think. Is
So the 418 that had an X train.
because it's just like this one liner here. Is you pick the test size, that's the percentage of the total. So it's 20% to the test. And then random states just so it's consistent. But yeah. Yes. And substantially faster too. Like the, all right, I can go back to what it was before. But like with the 6 layers with 750 neurons and then decreasing down, it took, like I said, I think it was around 1,000 to hit above 95%, but it took over 200 epochs for it to even move from that baseline accuracy. However, with Atom, with only 4 and much less neurons, it took less than 10 for it to reach over 97% accuracy. And I think if I let it run longer, it'd probably, well, actually, I would assume it's probably close to maxed out because Weka didn't even get much higher than that. Mm-hmm.
And I hadn't been hearing you keeping better with faster.
Yeah. Because what I'd guess is if I ran SGD with the more layers and the more neurons for many thousands, it would probably achieve the same amount. But it just took so long that I didn't feel like testing it through. Because Atom got the accuracy faster, so that's what I stuck with.
That's also great.
I did not try Atom there.
But it's faster. Same score. So almost based on both your data points there,
Yeah.
right? It almost seems like it's a smarter search in the mountain. Like I said, maybe the step size gets adjusted because that's useful, right?
Yeah.
If you're close to the bottom, maybe make the step size smaller.
Okay.
When you're above, make it bigger. So that makes sense. Also, I would say a better randomization. That's a better randomization. You go from I start here, so it's a smarter somehow.
So you mean with randomization, like where it drops those pins?
Yeah, exactly. Okay. Imagine like a mountain page for the pot of gold.
Yeah.
Right?
Okay.
So where you drop all the parachuters, right? Because if you put them in bad places, they'll never find. Okay. I know it's a dumb analogy, but it's kind of how it works.
Yeah, I think it gets the point across.
What else? But does that make sense?
Yeah.
Definitely look into. You guys have time. Find why is Atom faster than
okay.
And talk about it. But it certainly has to be that realm of looking for the optimize the minimum.
Yeah.
Remember it's not like a quadratic or guaranteed minimum neural nets. So lower, and there are multiple minimums. So you may actually be missing out on the global.
Yeah.
Give you that extra $1 million in stock.
That'd be a nice one to find.
I mean, it would. So you're missing out. But yeah, great question. Yeah, great job. All right. So
I'm recording it. So you need to share though, because it needs to. Your thing needs to appear here, or over there.
It's so weird from this side of the.
Yeah. It's okay. See now, so.
Okay.
And it's recording. Was it recording? Yeah. All right, guys. Let's listen to David's presentation.
So I did my data set is on credit card fraud. So in the data set, there's 284,807 transactions. And out of all those transactions, 492 were fraudulent transactions. So for this, I'm using logistic regression, which is like supervised learning. So let me just run these. And then I'm going to print out the first 5 rows. So the information on the time, that's when the transaction was made. The amount is obviously the transaction in dollars. And all the V's that you see, that's the features in the particular transaction. And then the class informs whether the transaction was legit or not. So If it's a 0, it's legit, and if it was a 1, it's a fraudulent transaction. And this is going to print out the last 5 rows of the data set. And this is going to give you the basic information of the data types of the columns. Right here, we're going to see all the null values. And as you can see right there, there's 28,400 and 284,315 that are legit and 492 that were fraudulent. And as you can see, it's very unbalanced, and you don't want an unbalanced data set because it could get like skewed to one other side. So we want to make it even. And then we're going to print. And then you're going to see that the mean for the fraudulent transactions is way higher than the mean of the legit transactions. As you can see right here, this is the fraudulent ones and the legit ones. And this line, it will just basically pick random rows from the legit data. And then basically we're gonna have a new data set with the same amount of rows for the fraudulent and legit transactions. So it could be balanced. So this would be the new first 5 rows. And the new last 5 rows. New data set.
So you're just picking making a balance.
Yeah.
So you have 492 of
Fraudulent.
fraudulent, and now you have 492 of non-fraudulent.
Yeah. So they could be balanced.
Why did you do that?
I didn't want to, I feel like if it's in balance, wouldn't it skew more towards one other? This is going to show the features basically. Print them out. The Y features. This is going to print out the shape of the X shape, the train shape, and the test shape. And then we're going to use the logistic regression model. And then on this one, we're going to fit the data into it.
Times 2 is 94.
Okay, and then this is, we're going to get the accuracy on the training data. This is, we're going to get the accuracy for the test data. And then we're going to get our results on this one. So for the training data, we get a 94, 95% almost. And then for the test data, we get like a 93, 92%.
Model, where's the train? Oh, model fit.
Yeah.
Train prediction. Okay, that's correct. And then you do model predict X test, Y test. Yeah. And then you print both. Okay, so yeah, 94 for train, 92 for test. Okay.
Yep.
How many features do you have?
I think it was, yeah, it was 28, I believe.
Like 30.
Yeah, 28.
Where's the neural net?
I didn't incorporate neural net into this one. I just used logistic regression.
So you might want to consider adding the
Neural net.
It's not difficult.
Mhm.
I can see your point that logistic regression works well. So why use a neural net? So there's that argument, which I would probably lose. But one question that's interesting: why did you? So you had 280 something thousand, right?
That were yeah.
Fraudulent, and then you have 492
that were fraudulent.
And you just balance it. The problem with that is that that does not represent the real data in the world. You know what I'm
Yeah,
saying?
because it's the more of a 50-50 now, right?
Yeah, you made that scenario, and I see what you did, right? But that's not real data. We don't live in a world, thankfully,
Where it's even.
half the transactions that we encounter are fraud.
Yeah.
That would be a really bad problem. we would get scammed all the time. And so that's not the reality of the world.
I know, yeah, I get what you
So I ask you this question, a more interesting question. I'm not saying what you did is wrong or right? But it's got implications.
That's because in a real world situation, it'd be different.
Well, the real world, as I said, it wouldn't be half the transactions. Yeah. So what's going to happen? So here's the question. Let's say you build this model, and you go and you sell it to some naive person in the bank, and they pay you $100,000 for it, right? Because they're clueless. But what's going to happen when they call you in a month and they tell you, you know what, we've applied this model, and this is what happens.
There could be some errors.
So well, it's not about the errors. Think about it like deeply. What would be, what's going to happen? Exactly. So you see that point? Yeah. Exactly. So it's just going to assume that more things are fraud. It's going to be more of that. You see that?
Yeah,
so it's going to start flagging out of, let's say that in a month they get 100,000 transactions, right? And it's going to start flagging 40,000 of them as fraud. What do you think they're going to do with your system? Because that means they have to let's say for legal, now they have a suspicion. So they just hired 40 people to go through this, and none of it was fraud. Do you see what I'm saying? Yeah. That's the problem with your system. So they're going to say, David, you know what? We're going to sue you. So what you want in this kind of system is actually the opposite of that, right? It depends, right? Yeah. So it depends on what it is. But the problem is like intrusion detection systems almost, right? They detect too much. People just ignore it. And so I'm not saying it's wrong, right? Yeah. But you have to think of there might be a scenario where what you did is actually the way to go. Yeah. You know, because you have the resources. It's like, in a war or something, right? So you have an absolute need to not miss anything. So there, your approach might be a little bit more, but here in fraudulent, not fraudulent, you got to find a balance. So really, what I would say for your analysis, the way that you should have started, leave the data as is.
Leave it as is.
But use a neural net. So that's where you're missing something. Because the logistic regression will probably not be able to crack this, but a neural net with a lot of layers, etc.
It's more.
Maybe. And that was what I was kind of hoping that you would do, is like show, well, here's the data set as is. And here's logistic regression, and then here's a few deep neural networks with a few different architectures. And guess what? This one architecture is the one that does the best. Gotcha. Does that make sense?
Yeah.
So I don't know if you want to try doing that, you can still do it on Thursday and see if you can make it work a little bit. Otherwise, make sure you put it in your report.
Okay.
And the reports are due the day of the final. So the day of the final is next Monday, right? Yeah. This class is at 12, right? So I don't know. We'll see the exam, but it's probably like 12:40, 12:30. we can do it online. Or you want me to come? But that's basically.
Okay.
But you see what
No,
I'm
yeah.
saying? So
Yeah.
it's an important choice. You guys understand? You have questions for David?
What's up?
About your data set
Yeah.
and your features are in the data set, the features are labeled B1
Mhm.
through 28. I wonder what they actually are.
Yeah,
And I wonder if that's public information.
it, on the Kaggle, it would just say that like. well,
Yeah, I
just
think
features.
actually you're dead on there. So I think it's just because of privacy things, they've actually converted it. That people don't infer things.
Yeah,
That makes sense, actually, but it could be for privacy. Yeah, exactly. All right, but yeah. Hmm?
Peter, we mad about that bearskin rug.
Yeah. But yeah, that's. All right, great, thank you. That's it. I'll stop the recording.